Hi everyone, welcome back to the CIERA Spotlight series. My name is Gideon McFarland. I'm a graduate student here at CIERA, and I'm joined today by Shanika Galaudage. Shanika is a CIERA Adler postdoctoral fellow, and so she spends half her time here at CIERA, half her time at the Adler Planetarium, doing research and science outreach. She's a gravitational wave astronomer by trade, and she studies the population level properties of compact object binaries. Welcome, Shanika.
So before we get into things, we should roll through some jargon. So first of all, compact objects. What are they? They are formed from massive stars. So if you take a look at this massive star, it's got a core. At the end of its life, it will undergo a process known as core collapse supernova. So its core collapses in a cosmic spectacle known as a supernova. And in this explosion, you end up with a compact object. So this can be a black hole or a neutron star, for example. So black holes, they're very extreme objects where not even light can escape these things, but they're also stretching the fabric of the universe in very extreme ways. So if you think of the universe as a fabric, like a trampoline, these black holes are stretching this fabric very strongly. And now I want you to imagine one black hole stretching it and another black hole stretching it. And then these objects going around each other around 60% of the speed of light. That's going to create some chaos in the universe. It's actually going to create these ripples that travel across the universe, and these ripples are called gravitational waves. So, gravitational waves. So they're ripples in space-time created by compact objects going around each other. And so we've got these ripples, and we can detect them here on Earth using the gravitational wave detectors we have around the globe. We've got 2 in the US, 1 in Italy, and 1 in Japan. And what's great when we have multiple detectors is that we can localize these sources on the sky. Just like when you're trying to figure out where a sound came from in the room, you've got your 2 ears, and it allows you to pinpoint where it came from. The more detectors you have, the more easily you can pinpoint things on the sky. It's the same kind of principle. But how do we actually detect these ripples? Well, we have to use these detectors known as interferometers. So interferometers you can think of as like a really precise ruler. Essentially what you have is 2 arms, and you've got this laser light that gets split and sent down these 2 arms. Each of these arms have 2 sets of mirrors where the laser light bounces back and forth and then returns and then is recombined at this photodetector or light detector. And essentially what happens when a gravitational wave passes through is that one arm gets compressed and the other one stretches, and vice versa. And this happens, and that's how we know a gravitational wave signal has passed through. And there are gravitational wave signals passing through us all the time, right? But this change in distance that I've demonstrated is pretty dramatic. The actual change in length of these gravitational wave detector arms is around 10,000 times smaller than a proton. So I think it's an amazing feat of engineering for us to be able to detect such tiny, tiny changes in distance. But once we've done that, and once we've accounted for noise in the detector and things like that, we can extract a gravitational wave signal that kind of looks like this. So essentially you've got these wiggles, and the wiggles get closer and closer together up until this point, and then it, I guess, flatlines. And so what this is showing is the evolution of the binary black hole. So as it gets closer and closer and closer, this is the in spiral phase, and then it merges. So as it gets closer and closer, it gets faster and faster, and that's why this frequency goes up. And then you've got the merger, when these things, and then you've got this region, it's a ring down when you've got the black hole, and it's kind of ringing down to a steady state. And so what I actually do is I take this gravitational wave signal and I extract properties about the compact binary that merged, because this signal actually encodes information about how big these black holes were, even how fast they're spinning, and somewhat the direction they're pointed in when they're spinning. So what I do is analyze the signal to get those properties of each of the binary black holes. But we've seen more than 100, or around 150 of these black holes thus far, or pairs of black holes. And so what you can do with many, many detections is you can actually do a census of these black holes. Because it turns out when you look at the population properties of these objects, you can actually start to understand the kinds of environments these objects live in, but also more about the massive stars that produce them in the first place. So that is really the bulk of my work, where I look at binary black holes to better understand their lives and the massive stars that produce them. So with that, back to the interview.
Okay, so let's start with a little bit more about your path to astronomy. So can you tell us a little bit more about your story, how you came to astronomy, things like that?
I'm going to try and keep it short, but we'll see if it's a long journey. But my earliest memories of being interested in astronomy was when I was in primary school. So I think I was like 6 or 7 years old, and I really enjoyed learning about the planets of the solar system. And one of my earliest memories is going to the library, the local library, and wanting to borrow all the books on all the planets. So 9 books at the time, because Pluto wasn't demoted yet. But the librarian told me I could only borrow 5 books from a certain series. So I was a little bit upset, and my dad had to calm me down. So that is my earliest memory of being interested in astronomy, but I don't quite remember or know why I originally liked planets. I also loved going to the Science Works Museum in my hometown. So this is like a museum that showcases a bunch of sciencey things, as well as the Melbourne Planetarium. So it feels like almost a full circle in terms of coming here and working at CIERA and the Adler Planetarium. So I absolutely enjoy being able to like communicate these things at the planetarium as well. But going back to like how I ended up here, I think I've had a lot of people along the way kind of nudge me in this direction, and not in a way that, you know, pressured me or anything, but more to do with, you're interested in this, Shanika, why don't you just do it? So for example, through primary school, I thought, you know, the only thing you could do if you're interested in space is become an astronaut. I know now that's not correct. You can be an astrophysicist. But when I thought, don't want to be an astronaut, I'm very happy with my feet on the ground, and astronauts can do the brave things and go to space. And I thought, okay, I'm probably going to just, you know, do medicine or something, because that's what I saw people like around me do at the school I went to. And then I moved schools, and then my high school teacher, who happened to end up being my physics teacher, was like, Shanika, if you like physics so much, why don't you just pursue it? It sounds so silly to say it out loud and kind of cliche, but that was really a light bulb moment for me to take this seriously and go, actually, maybe I could study this. And so until someone showed me that that is an avenue, I had no idea, really. So I did some more, you know, research into what I could do in uni and decided to major in astronomy, maths, chemistry, and a bunch of other things. And then it kind of all fell into place along the way. I just continued doing physics and astronomy, and I was torn between the two. In terms of physics, I was like, but there's quantum physics and condensed matter physics and particle physics, and couldn't decide until I did a 3rd-year research project. And it was all about neutron stars. So neutron stars are probably my favorite compact object. They're really dense things, such that if you were to scoop up like a handful of this matter, it would weigh more than Mount Everest. Or like if I tried to fit it in this mug, that would be like trying to carry around Mount Everest, and I don't think anybody can do that. And so these extreme objects, physicists want us to study these things because they're like high energy physics labs in space. And I was really intrigued by them. So I continued doing a project in that, and then went on to do honors in that same area, studying these neutron stars. And then by that point, my supervisor at the time for this honors project noticed that I was interested in this hot new topic called gravitational wave astronomy. So to put this into perspective, I started university in 2014. My honors project was in 2018. The discovery of gravitational waves was announced in 2016. So there was a bit of time for me to get to know it, but I had no idea I'd be working in this when I started university. And so he kind of nudged me and went, you're interested in it. And I got a bit too comfortable in that project. I felt scared almost to go back to square one with my PhD. But I did, and I'm glad I did, because I absolutely love the research area that I'm in today. So I did my PhD in Monash University in Australia, did a postdoc for 2 years in France, and now I'm here. So
that's a great journey. Thank you for sharing. Sort of on the lines of some of what you said, talking about how you couldn't borrow all the books in the library, challenges in your journey. Can you tell us a bit more about those challenges, how you overcame them?
Challenges of books too. Challenges. I think the main challenge that I've had through this entire career thus far is actually my mental health. And so I remember in high school, I missed a few months of school, really, from mental health issues that also resulted in physical health issues. And I never really dealt with it back then. I just thought, you just keep going. And not having dealt with that, then I kind of crashed and burned in university. So I really had to learn how to regulate these things. So the main thing I suffered from was extreme anxiety. So this really prevented me from sitting any timed assessments such as exams, which, a huge portion of one's grade. And so I ended up doing my third year of university across 2 years because I had to repeat some subjects, but also work slowly my way up. Thankfully, I had people in the university who noticed, particularly admin staff, who were like, there's something up with you. We really think you should seek some help. And I did. And so since then, I've been really working on this. Thankfully, I don't have to do exams anymore. I might have to write them someday, but I really had to step back from putting so much pressure on myself. And these days, I really try to go with the flow. Don't really, worry too much about what comes next. Just enjoy the day-to-day. Because if I think about it too much, I will probably fall back into that rhythm, which I don't want. So my main challenge definitely was overcoming my own mental health issues. Well, still dealing with them today, but not to that severe extent. So it's something that I am really trying to be better about in terms of just being kinder to myself.
Yeah, I feel like mental health is really a big issue in academia nowadays. So thank you for sharing that story and for telling us how you overcame that challenge. I'm a little curious to hear a little bit more about what it was like, not really knowing exactly what your research would be in university. So you mentioned, gravitational waves were sort of discovered while you were in university. You kind of like hopped onto that train. How was that process like?
Yeah, definitely hopping onto the train is the right phase. I was like, yes, this seems so exciting. But I have to admit, I've always been interested in the more extreme side of astronomy. I remember even in high school, there was a project that I did in year 9. That was a research project that we had to think of a question for. And my question was, black holes, white holes, wormholes, do they exist? And if so, are they a threat to humanity? I don't know why that was my question, but I've always been fascinated about this idea of the fabric of space-time and how everything in it is stretching space-time. And gravitational waves are these ripples in space-time, and just felt like something that I really wanted to do. But I feel like what I've taken away from that as a researcher and things like that is just to really jump on the opportunities that come by, because you really don't know what area of astrophysics is going to, or any area of research is going to exist in 10, 20 years time, or like however long you have until you go to university, for example. So I had mentors who were also, you know, very flexible to me moving around and not, you know, possessive of their students, for example. They were more than happy for me to jump from one project to another. And so having that kind of mindset of, or building that mindset, because I didn't have it to begin with. Mentors helped me build that mindset of being able to jump onto these new opportunities that just come your way. I think is one of the most exciting things about astronomy, just the new things that come up and being able to, I guess, pivot. And I think, honestly, that also makes me a better researcher, I feel, like being able to pivot and jump on these new opportunities as they come by. But yeah, that was definitely, like, I'm so happy we discovered them in 2016. Well, announced the discovery in 2016. They were technically discovered in 2015. But I feel like there was also like right time, right place, right university, because Monash University has a strong gravitational wave group as well. And so I did my PhD there, and it really worked out in a way. So
great.
Yeah.
Yeah, it seems very serendipitous, the whole situation, which is amazing. But I'm also really interested in your day-to-day life.
So very unique role where I spend 70% of my time doing research, 30% of my time doing outreach, but it's 50% of my time at each institution. I will admit it's a little bit tricky. I feel like I'm doing two jobs. And even though I've been here for over 6 months, it feels like I've been at CIERA for 3 months maybe. And so I do struggle actually with feeling like I'm really embedded in the community when I spend part of my time there. But I also get the best of both worlds in the sense that I'm able to do research here in this like diverse department and work with different groups and people. But at the Adler, I have this really unique opportunity to be able to communicate things to the public. For example, right now, I am helping with some floor talks about the moon because we're in the Artemis missions are coming up.
Apologies for this interruption, but we have some breaking news.
And so I get to both work towards my passion of research, but I also get to spend part of my week communicating to the public or working on things that are deliverables to the public, such as contributing to exhibits and things like that. So it's a really exciting time for me, but I also have to be careful that I don't spend too much time on one or the other. I also do outreachy things for the collaboration as well, which I really enjoy. So that's kind of where I'm at with this postdoc of just, I feel like I'm still a little bit in the exploratory stage where I'm really trying to figure out exactly what I'm going to be doing. But that 50-50 split, still navigating, but really enjoying.
Yeah, that's great. That's so interesting. But also I know, so you talked about science communication and like doing outreach. I believe, so our next question is about, you know, what you do outside of research. And I think you brought something to show about your outreach. So do you want to show us that?
I would love to talk you through this. So this is show and tell time. This is the binary black hole chunk chart. I don't know if you've seen that cat meme. Have you seen that cat meme? Okay. Well, there is a meme that takes you from like slim to chunky cats, but I'm taking you from like slim to chunky black holes. And so actually, if you look at this curve here, it's showing the real mass distribution of black holes. And so there are different features here. And these are the kinds of features I mean when I say we're getting more and more information about these black holes. For example, we know there's a lot of black holes at around 10 times the mass of our sun, 10 solar masses. And then there's like, seems to be some sort of bump over here. And I think we have an idea of what this means, but we're not quite 100% sure yet. And there are also these regions where we see black holes where we didn't expect to see them before. And so to me, like, I like being able to create things that the general public might be interested in looking at. And this is like one of the things that I spend my time on, not just in a professional setting, but also just because I find it fun. And I'm hoping to do more of this as I work at the Adler as well and maybe contribute to exhibits that way. But really, it's just, you know, posting some more informal things online from time to time to be able to communicate some of the scientific results, but in a fun way. And yeah, I just find this stuff to be so much fun. Yeah.
Okay, so the interview is almost over. We have 2 more questions for you. It's kind of future looking and one fun. So our second to last question is, what are your plans for the future? Just in general, where do you hope to be in the next few years?
I mean, if we can talk about ultimate dreams, my ultimate dream is to be able to do both research and outreach in a professional setting forever. Where that might happen, don't know. Roles like this are rare, and so I shouldn't put all my hopes in it, but I am absolutely going to jump at any opportunity that comes my way. I've really hit a stage of, again, going with the flow kind of mentality is what I've reached, because I feel like it's healthy for me, both in terms of managing my mental health, but also it's very hard to predict what kind of career you're going to end up in. I feel like I really strive to have the approach of just enjoy the day-to-day and try and, learn something new, do those things, and just really have fun. And I feel like it's hard to do when you think about the future and you think about career prospects and things like that. But the wisdom that I'm getting from other people as well is that don't worry too much. There's not much you can control. What you can control is the day-to-day that you have. And so when I think about the future, I'm really thinking about maybe max a month ahead. I know that I will have this postdoc till the end of, August 2028. And so until then, I will really try to make the most of this opportunity, because this postdoc is pretty unique. And so I will very much try to make the most of it without burning out, because that would be bad as well. So that's as far as I'm thinking into the future. Like, I have plans until September 2028, and we'll see what happens. I'm just going to look at any opportunity that comes my way and see if I enjoy it.
Okay, that's great. So our last question, a fun one.
Okay.
So if you can teleport anywhere into space for a few minutes, just like teleport there, take a look around, have some fun, and then come back safely. If you're on Earth, to the share, right back to the share, teleport from the share somewhere, go right back here. Where would you go in all of space? Where would you teleport?
I have a clarifying question. Anywhere in space and time, or just space?
We'll say just space. We'll say present day space.
The reason I ask is because I think I want to be slingshot around a supermassive black hole, right? Because have you watched Interstellar? One of my favorite movies. Essentially, when you go towards things that are more and more massive, time slows down for you because of general relativity, because of how time behaves. Time is all relative. Everything is relative in the universe, right? And so if I'm slingshot around this supermassive black hole and come back, then I'll be in a different point in time on Earth. And I think that would be really cool to see the future of Earth. But I also want to be brought back to this point in space and time, because I think it would be very sad also to not have everything that you love still be around. So I feel like I'm cheating a little bit. I'm doing some time travel here. But I'd like to be slingshot around a supermassive black hole to see what Earth is like in the future, because we might have, bases on the moon, bases on Mars. So that would be cool to see. But I want to be back in this chair in this point in space and time, because I really like my life right now. And I like being able to experience now and not lose the things that I enjoy at this moment in time. So yeah, I think I cheated there a little bit.
No, that's fair. That's a fair answer, and it's a great answer. Yeah, but thank you so much for being here, for being interviewed. And thank you, audience, for watching this video, and hopefully see you in the next episode. Bye for now.